All right, so now let us look at the support vectors one more time. So a maximal margin classifier tries to find the separating hyperplane so that all training observations are on the correct side of the margin. So not only on the correct side of the separating hyperplane. So if this is our separating hyperplane, we have some observations of one class on this side, observations on of the other class on this side, right? So they should be not only on the correct side of the hyperplane, but also on the correct side of the margins. So these are the margins. Soft margin classifier allows some observations to be on the wrong side of the margin or of the even of the hyperplane, right? And these observations are going to be misclassified. So it is going to tolerate some degree of misclassification. And so because the maximal margin classifier just may not exist if the two classes are not linearly separable, then a maximal margin classifier just may not exist. But a soft margin classifier always exists. So training observations that are exactly on margins or between margins are called support vectors. So for a maximal margin classifier, since there is nothing inside, so it looks like this. So there is like our separating hyperplane. So then these are our margins. And then there's going to be some training observations here, some training observations here. So usually there are 2 or 3 support vectors. For a soft margin classifier, there's going to be more. So probably some of them are going to be inside the margin, some of them on the wrong side of the margin. Something like this. So this classifier only depends on support vectors, which sometimes is convenient if we, I don't know, if we trained it once and then we got a new bunch of some new data, right? And we are considering whether we should retrain our classifier. And if new data is not within the margins, then we do not need to retrain the classifier. This soft margin classifier, it has this parameter, the cost, so which represents the cost of misclassification. So this large cost means the cost of misclassification. Misclassification. And now, of course, the bigger is the cost, the less forgiving our classifier is to misclassification. So, and if it is less forgiving to misclassification, it means that margins are going to be narrower. So hypothetically, so the limit of our classifier as C goes to infinity is going to be the maximal margin classifier, so the separating hyperplane. But usually a separating hyperplane just doesn't exist. So still, a large cost means narrower margins, and narrower margins means fewer support vectors. So here you see 12 support vectors. Well, actually, if you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, you will only find 9, but this is because some of them are duplicated, right? So I don't know. So maybe there's going to be like 2 observations in the training set with the exactly same values of x1 and x2. So the actual number is 12. Yeah. So if you make it a little bit smaller, then margins become wider. And at the same time, it means that, of course, there will be more room between the margins. So there will be more vectors inside the margins, and they are support vectors. Yeah, and by the way, misclassification is only allowed within the margins. So outside of the margins, everything is classified correctly in the training set. But within the margins, we allow misclassification. So smaller cost, more support vectors, and so on. So the higher is the cost, the more support vectors we have. So this is a very small cost, and now it means that our classifier is very forgiving to misclassification. So we have 50 support vectors, which is basically half of our data. All right. In any case, the decision boundary is a linear, well, is linear, is a hyperplane, and we can represent this linear support classifier in this formula. So this is f hat. So initially, recall that initially what I had here is alpha I times x transposed times xi. So I just replaced x transpose times xi, which just means the dot product of the vector x and the vector xi with this expression x comma xi. This is the same thing, only the first is in the matrix form, the second is in vector form. And it turns out that alphas here are non-zero only for support vectors. So the final classifier is this sum where the sum is taken over the set of support vectors. Okay, so this was all about support vectors.